In this video, we're going to talk about the hypothesis test that we're going to do for the relationship between two quantitative variables. We're going to be doing a hypothesis test for slope. We will actually only be doing a hypothesis test for slope and not a hypothesis test for the y-intercept. The reasoning behind this is slope is actually the relationship between x and y. It tells me as x gets bigger, what happens to y. The y-intercept gives me no such indicator of a relationship between x and y. Our null hypothesis, when we do a hypothesis test for slope, will be that the response variable is not linearly related to the explanatory variable. What that will actually mean for us, this equates to a slope equal to 0. And what a slope equal to 0 looks like, as a reminder, is that you just have this horizontal straight line. So what that means is that x is getting bigger, it's having no impact on y, and thus there would be no relationship between the two variables. Our alternative hypothesis will just simply be that the response variable is linearly related to our explanatory variable, or think of this in the slope idea is that the slope is not equal to our 0. Step 2 will be the same as it was before. We will always reject the null and believe the alternative when our p-value is less than alpha. Step 3 is our other big place where things change. Let's first talk through those conditions. First, written out, you have sort of the long version of the condition, versus in the parentheses here, you have the shorter version of the condition. So our first idea of the conditions is normality. So at each value of x, the distribution of y is normal. So we need things to be normal. Second, for all values of x, our standard deviations of the distributions of the corresponding values of y in our populations are the same. What that really means for us is that we have this constant and same standard deviation. This is very similar to the condition that we had with analysis of variance. Our third condition is that our values of y are random and independent from one another, so they are not affecting each other. Once the conditions are met, I can calculate my test statistic. Now I've given the test statistic in a more StatCrunch friendly form here versus doing the full formula for it. First, it is going to be a t, just as we've seen before, right? So a t is still looks like that normal curve, not quite a z type idea, still centered at 0. B1 is just our sample slope that we get. We technically are subtracting off 0 here because of the idea of the slope being 0 as our null hypothesis. And then we're going to be dividing by a standard error. So this is sort of showing that same typical form that we've seen for a test statistic as we have our sample value minus the value in the null hypothesis divided by a standard error. There is a mathematical formula to calculate that standard error, but we're not going to be doing it. What you'll get to see here is that standard errors will automatically be given to us in StatCrunch. So learning that formula makes no sense for us when we're already going to have that calculation done. Once we have our test statistic, we get our p-value, which again will actually come from StatCrunch. And then be able to make our decision based upon step 2 and make our interpretation and conclusion from there as well. In the next video, we'll apply this to our first example.